Today's topic is on electric charge, Coulomb's law, and electric field density. And we use the letter E for electric field density or intensity. Okay. So electric field intensity, we use the letter E, and very often we drop the letter intensity. We just talk electric field, and that is normally understood as we're referring to electric field intensity. Okay, so there are two terminology that use in this subject. One is called electric field intensity. The other one is electric field density. Okay, so E is referred to the intensity, and normally in short we just call it electric field. But the other one is the electric field density. We use the letter D, but we will come to that later on. Okay, so to differentiate electric field, we normally use the letter E, and electric field density, we'll use the letter D, which you'll come across later on in my lecture. The learning outcome from this particular lecture, what you expect to know at the end of this topics, you need to know how to use Coulomb's law to calculate electrostatic force, and use vector with Coulomb's law to solve electrostatic problem. Draw and calculate electric field. Okay, so this is very important. You need to know how to use vector. So not just calculating magnitude of force, you need to know the magnitudes and the direction of the force as well. You need it to be in vector. Electric charge, normally denoted by the letter Q, either capital or small letter Q. Doesn't really matter. Very often you use either or. Sometimes refer to electric pole, measured in SI units, coulombs, after the scientist Charles Coulombs. So your charge units is normally in coulombs, which is the SI unit. 1 coulomb is a very large amount of charge. So we normally dealt with very small charges. So where 1 coulomb is rather large, and we seldom or encounter things that measured in coulombs. So either we use things in nanocoulombs, nano is 10 to the power of -9, or in micro is 10 to the -6. So that is the range of the charge that we normally use or encounter. So electrons, if we have an isolated electrons that has 1.6 or roughly about 1.6 to the 10 to the -19 coulombs. So one electron charge magnitude is very small, 10 to the -19 coulombs. Object is negatively charged if it carries excess of electrons. So you study that in physics. So if you have an atom, if the atom is negatively charged, which means that it has more electrons than protons in the atoms. Okay, so it becomes negatively charged. If it's positively charged, which means that it's deficit of electrons, so which means that the atom has less electrons compared to protons. So normally the charge that can be moved is the electrons. So we can move electrons from the atoms, but we can't move the protons. Protons is fixed. Okay, so it's either the protons have more electrons or you have less electrons. So the one that we try to move is the electrons. Flow of currents, you study that in circuits. So we normally, in electronics or electrical circuits, we always look at the current. So if you have a circuit, I'm sure you studied this, let's say a circuit, let's say you have a resistor, we always said that the current flow. Okay, so current flow is conceptual, it's not real. Okay, the actual flow is the electron flow. The currents, you think of it as if it is a more positive charge that's flowing around the circuits. But as I said, positive charge proton doesn't move. It's the electrons that move. Okay, so it's the electrons that flow in the opposite direction that give rise to the current flow. It's what we call the current flow in your circuits. So the actual things that is flowing is actually the electrons, and the electrons is flowing in the opposite directions that give rise to the current flow. A DC electric current of 1 ampere is the flow of 1 coulombs of charge per second. And that is equivalent to 6.3 times 10 to the 18th electrons flow per second. So 1 ampere is a rather large current in DC. Okay, in your lab, very seldom you actually use 1 ampere in your circuits. So I'm not sure whether you have done any experiments in your circuits trying to measure currents. Normally you measure it in milliampere. Okay, we don't measure it. We don't have these. We don't do experiments in circuits at DC going up to 1 ampere. There is rather high current. And we're going to study flow of electrons in magnetostatics, which is a topic that we'll cover later on in this module. So what we're studying in the first few topics in this module is on electrostatics, that is on charges at rest, so which means that the charge doesn't move, or static charge. Okay, so that's the background about what charge is and how they behave. So Coulomb's law, the basic law of electrostatics. If we have Q1 is fixed at the origin, so we fix Q1 at the origin O, and if you have another charge Q2 that places a distant r away from the origin or from Q1 that has a position vector of r. Okay, so this is the scenario. So Q1 is at the origin, and then we have Q2 that is a distant r. So this is a distant r from the origins, and we can draw a vector r pointing from the origins to Q2. Okay, so that is the scenario. And what Coulombs or Charles Coulombs have found experimentally that each of these charge will experience a force, and that force is acting in the opposite directions. Okay, so if we have, let's say, plus 1 nanocoulombs plus 1 nanocoulomb charge at both ends, so this is equal magnitude charge, a force is experienced by the charge in the opposite directions, and that was found experimentally by Coulombs. And the force magnitude is given by Q1, Q2 over 4 pi epsilon naught r squared. Okay, so this is the magnitude of the force. So F1, so charge 1, you experience a magnitude force of Q1, Q2 over 4 pi epsilon naught r squared. Same as Q2, we experience the same force. So both charge experience the same amount of force magnitude. Okay, so I put down here as 1 coulombs, 1 nanocoulombs, and 1 nanocoulombs. So even if I change it to 2 nanocoulombs, so the force F1 and F2 is still have the same magnitude. Okay, doesn't mean that Q2 has a larger charge, Q2 will experience a larger force. No, it experiences the same force. Okay, so it depends on both charge, the multiplication of Q1 and Q2. So it doesn't matter what charge magnitude is, the force encountered by both charge is the same magnitude. And that is equals to Q1, Q2 over 4 pi epsilon naught r squared. And r is the distance separating between the two charge. Epsilon naught, there's a universal constant that is called permittivities of free space. Okay, so that's the formula for Coulomb's law in terms of its magnitude. But we know that the force is a vector. So in this example here, we associate the vector by the directions of the force that is pointing away from each other. So the magnitude is this, the direction is pointing away from each other. So you have two charge, and then the force will be acting away between the two charge. So this is known as Coulomb's law and can be written vectorially in terms of the unit vector AR along the vector R. Okay, meaning that if I go back to here, if I define a unit vector here as AR, and my unit vector is in the directions of my vector R, and earlier on I said that my vector R is pointing from the origin or pointing from Q1 to Q2. That's the direction of my vector R. So we can define a unit vector here, vector R, or we can mathematically write down my unit vector R. That will be my vector R divided by, you still remember unit vector? The magnitude of the vector R. Okay, so that's my unit vector. So unit vector means that a vector has a magnitude of 1. Okay, so putting back that into our equations, we can write down Coulomb's law as a vector. Okay, so F2 is equals to minus F1 because now we define it as a vector. So F2 will be in the same direction of my AR, but my F1 is in the opposite direction of my AR, my unit vector R. So remember, we have Q1 at the origin. My vector R is pointing to my Q2, and we define our force F2 and then our force F1. Okay, you can see that my force F1 is in the opposite direction of my unit vector AR. So we have a negative sign there. Okay, F2 is in the same direction as AR, or my unit vector AR. Okay, so my F2 is in the same direction of AR. And the universal constants that I mentioned just now, the relative permittivity epsilon naught is equals to 8.854 times 10 to the minus 12, and the unit is farads per meter. So it's good if you can remember this, but if you can't, if in assessments, you'll be given what this universal constant is. But if you do a lot of calculations, do a lot of example, eventually you'll remember the value. Okay, so that is the Coulomb's law in vector. So things to remember: if you define two charge, the vector directions. So normally we define 1 as the origins, so the vector pointing from 1 to 2, and then we define F2 to be the same direction as the vector, the position vector R, and then F1 to be the opposite directions. So if the charge is both the same magnitude, you can see that this vector, this Coulomb's law in vector will sort itself out. So if I have Q1, Q2 positive, then we know that equal charge of same magnitudes will expel. Okay, it will be forcing each other away from each other. So F2 will be in the direction as we expect it to be. But if we define Q1 as positive, Q2 as negative, then we know that opposite charge attract. Okay, so if you put it into this equation, so if I have Q1 positive, Q2 negative, then my F2 will end up be negative. So we know that whatever we calculated, our F2, now our F2 will be, because it's negative, so the actual force is actually in this direction, because they are attractive force, because one is positive, the other one is negative. So if you work it in vector, then putting in the value or the magnitude of the charge into the equations, it will automatically sort the direction out itself. So you don't have to intuitively trying to figure out how the force act. As long as you use these equations, okay, so this is a standard definition. You have 1 that is pointing towards 2, and that will be your directions. And then both force you define to be against each other. So F2 equals to minus F1 in vector. And then putting in the right value of charge with the positive and negative signs of the charge, then it will sort itself out. The SI units of the force is in newtons. Okay, I'm sure you know that the unit of force is in newtons. You probably learned that in physics. The same for your electrostatic force is also in Newton. Okay, so electric force is, or your electrostatic force is inverse square law force, which means that the force is inversely proportional to the square of the distance. Okay, so this is called an inverse square law force. And the other inverse square law force is, do you remember? You studied that in physics probably. It's gravitational force. Okay, so that also has an inverse square law, very similar to this equation. Instead of the charge Q1, Q2, in gravitational force, you probably have the mass M1, M2. Okay, and also inversely proportional to the distance. And then you have some constant multiplied by that. So very similar type of force. Okay, any questions up to now? So that is your Coulomb's law. And we're now going to look at an example, how we can use this law to make some calculations. So this example, we have a charge of 10 nanocoulombs. It's a distance of 0.5 millimeters away from a charge of -3 nanocoulombs. What is the magnitude of the force on each charge? So scenario, we have 10 nanocoulombs. And then we have another charge, which is -3 nanocoulombs. And then the distance between them is 0.5 millimeter. And then you ask to work out what's the force. So if I define this as Q1, this is Q2, then my force F1. So here it's not asking for a vector, just the magnitude. So we know that the magnitude of the force F1 will be equals to F2. And that will be equals to the equations Q1, Q2 over 4 pi epsilon naught r squared. Okay, so just put that into your calculations, and then you can work out the magnitude of the force. And then intuitively, you can work out the direction of the force as well. We know that one is positive, the other one is negative. So we know that this is an attractive force, which means that the force will be in this direction. Okay, so if you put that into your calculator, F1 equals to F2 equals to Q1, Q2 over 4 pi epsilon naught r squared. Put in the value, you get roughly about 1.08 newtons. Okay, so this is a simple one. So this is just calculating the magnitudes, and then you figure out the directions by intuition. But this is not what we want in this module. We want you to be able to solve it using vector. Okay, so we want you to define vector and then calculate vectorially. So we can repeat this. Okay, we do a similar example as one, except this time we use vector to do it. So let's put the charge 10 nanocoulombs at a position vector R1. So we define our origins here. And then we have Q1 will be in three-dimensional space that has a position vector 1, 1, 1. So meaning that if I want to draw this in my 3D space, so we have a vector something like this. Okay, so we have 1, 1, 1, and then we have our Q1 here. Okay, so if we were going to draw it in three-dimensional space, but that is very difficult to do on paper. Okay, so it doesn't really matter. We don't have to do it. So we just put that into 2D. We just write down the vector itself. So my R1 will be equals to here, which is equals to 1, 1, 1, meaning that my R1 in vector will be equals to unit vector of x plus unit vector of y plus unit vector of z, or in short, I can write it as 1, 1, 1. Okay, so that's the same thing. And then our vector 2, R2, will be equals to 2, 1, 0. So my R2 is 2, 1, 0. Or in the full vector form, that will be 2 ax plus ay, and then doesn't have the direction. So in the z directions, doesn't have a magnitude. Okay, so I'm sure you learned vector before. If I have two vector, R1, R2, I want to work out this vector here, R. Okay, so this vector R will be, if I reverse this vector, that will be minus R1, and my R will be R2 minus R1. Okay, so I sum the two vector, minus R1 plus R2, give me my vector R. So same thing here, my R will be equals to my R2 minus R1. Okay, so you can put in the value 2, 1, 0 minus 1, 1, 1, and this gives you 1, 0 minus 1. And that will be my vector R. Okay, so I know my vector R. I can work out my unit vector R. And then you can apply it to Coulombs law. The vector one, the Coulombs law with the vector. So my R vector is 1, 0, minus 1, the magnitude. That will be square root of 1 squared plus 0 is nothing there. So minus 1 squared. That will be 1, 0, minus 1 over square root 2. And that's my unit vector AR. And the formula for our Coulombs law, that will be F2 in vector equals to minus F1, that will be Q1, Q2 over 4 pi epsilon naught R squared. R squared here is referred to the magnitude, which is times our unit vector R. So this will be in millimeter as well. Okay, do you get all that? Then you can then solve the vector force F2 and F1. Okay, like before, we can calculate what is the magnitude of the force, which is Q1, Q2 over 4 pi epsilon naught R squared. And R, as I shown just now, it worked out to be √2 millimeters. That's the distance between Q1 and Q2. And then the force will be 0.14 AR unit vector R. Okay, so I have also shown you what is AR just now. Okay, so you can put that back into this equation here. Then you know exactly what's the force in terms of vector. I think something not right with this example. Okay, so the error is here. So you should have defined this as F2 equals to minus F1. So our F2 should be defined in this direction and F1 is in this direction. And this should be equals to, instead of using a magnitude here, this should be equals to minus 0.14 of the unit vector R in newtons. Okay, so if you do that, then my F2, although the answer that shown just now is the same, but it's inconsistent with what I said earlier on by defining the vector R, F2 to be in the direction of my vector R. Okay, so that only confuse the definition. So this is the wrong way to define it. We should have defined F2 in this direction and F1 in this direction to be consistent with the earlier equations that I shown. Okay, then now you can put in the values of Q1 and Q2 exactly with the sign as well. Okay, so that will work out to be equals to minus 0.14 unit vector R. Okay, so do you understand what I said? Why I have to change it? Because earlier in my lecture, I said that we always define Q1, Q2. If this is my vector R, we always define F2 in the direction of the vector R, and then F1 in the opposite directions. And then if we do that, then we put in Q1 and Q2 exactly what they are, the sign, then the equation will sort out itself. Because if you do this, then we have to intuitively know where the force is. Okay? Because now we put magnitudes there, so then the sign of the charge doesn't resolve itself in the equation. So it defeats the purpose of vector. But if you define in this way, so if the charge is positive, then F1 and F2 will be in the direction as you define. But if Q1 is positive or Q2 or either one of them is negative, then the outcome will be a negative vector. Then the force will be opposite to the direction as you define. Okay, so it will tell you exactly what the direction is. Okay, so this answer here is still correct. So putting in the unit vector into the equations, then you end up with this is the force, or in the full vector, you can write down this is equals to 0.096 unit vector x minus unit vector z Newton. Or in your maths, you said that this is I, and then this will be K. Okay. Okay, so that is Coulomb's law. So if you know how to solve this using Coulomb's law in vector, then you will have acquired the learning outcomes of Coulomb's law. So if I go back to this example, Okay, so you are given charge in unit of position vector. So if I change the position vector, change the magnitude of the charge, I'm sure you know how to calculate the force using Coulomb's law. Okay. So let's say I make this to 2, 1, 0. So you just change that accordingly to work out the force. Okay, so again, go back, work out R, and then work out the unit vector R, and then you can find the force if we move the charge 10 nanocoulombs to this position vector. Okay? Do you think you can do that? If I change that to 210, you can work out the force? No? So all you need to do, okay, bad example because I put both the charge at the same location. 310, okay? So all you need to do is change my 111 to 310, calculate R, work out the magnitude of R, work out the unit vector R, and then put all that into this equation here. Okay? And then you can work out the force as a vector. Okay, so that is how you go about doing it.